Welcome to Seattle Atheist Church. I'm glad to see everyone here today. Free thinkers, questioners, non-believers, atheist curious, whatever you like to call yourself, you are welcome here. At Seattle Atheist Church, we call ourselves an atheist church because you will never hear anything supernatural promoted from the podium. The coronavirus has affected us all in one way or another, and we hope that people are doing well. The safety of our members is very important to us, and so we thank you for joining us online. And now our creed. Seattle Atheist Church was founded on the principles of scientific naturalism and secular ethics, which commits us on the one hand to reason and evidence-based thinking, and on the other to compassion for our fellow human beings. These commitments motivate us to oppose magical and wishful thinking and all forms of dogma, as well as to stand firmly against all forms of prejudice. Truth claims are attempted here, and we stand ready to revise our thinking in light of new information. We attempt to be excellent to other conscious beings. We believe in good because good works in non-mysterious ways. If that sounds right to you, then you are probably in the right place. Please join me in welcoming Emma, who is going to give us a talk entitled A Universe from Nothing. Emma, you have the spotlight.
Thank you. Let me see if I can share. Okay. Hi, I'm Emma Chase, and I'm excited today to be talking about how it's possible to have a universe exist even if there was nothing before and without any sort of supernatural intervention. This talk is largely based on a lecture by Lawrence Krauss in 2009 and the subsequent book in 2012. The video of the talk is available on YouTube. And I encourage you to consult the lecture or the book for clarification on anything you don't get. And it's just, if you can't get hold of me. He's probably better one to answer the question. Anyway, so people have always wondered why there is something rather than nothing. Where did it all come from? Well, the easy way to answer that, one way to answer that is that there has never been nothing, that the universe has always existed in one form or another. Theists, of course, would say God created it all, but there's no real information in that answer because it begs the question of how God came to be with the powers to create a universe. Much simpler to say the universe has always existed, but it's not a very satisfying answer. So there's an alternative explanation. Could the universe have come into existence all on its own from nothing? How could that happen? Although we are far from being able to tell everything about the early universe, recent cosmology has been making it plausible that the universe did spontaneously come into existence. Quantum mechanics suggests that the condition of having nothing at all, that is, no energy, no matter, or space, is unstable, like balancing a pencil on its point. A condition where small quantum fluctuations are enough to cause the decay of this nothingness into energy, matter, and space. That is to have nothing fall into a state of being, the Big Bang. This is by no means proven, but new discoveries seem to be leading in that direction. So what are the conditions that point to something from nothing? First, we would like to have no space in the universe at the Big Bang to start off with. And we'd like to have zero total energy, because if you had some energy, then where did that come from? So also we'd like to have a flat cosmic geometry to the universe, since it's likely needed for zero total energy. Finally, we've learned about virtual particles, and that they can give energy to empty space. And the process could spark the Big Bang. Okay, so I'll go into these conditions and say something of what has been learned about them and why they're likely true. I also see no convincing evidence requiring the existence of anything before the Big Bang. And while this does not prove a universe can arise from nothing, it is highly suggestive, and at least in my mind, most plausible reason. Okay. So in showing this, let's start with what was thought of the universe 100 years ago. The conventional wisdom was that the universe was static and eternal. Galaxies were unknown. The Milky Way was thought to be the whole universe. So when Einstein formulated general relativity, he came up against a problem. That is, gravity sucks. It only pulls, it never pushes. So all the stuff in the sky would collapse on itself. Everything would collapse on itself. Einstein was able to change his theory to accommodate that. Let me show you in a user-friendly fashion. This is for philosophers. Only kidding. The left-hand side in general relativity tells you about the geometry of space. The right-hand side represents the energy and matter in that space. The theory equates the two sides, indicating that space is curved in the presence of matter. Here are the Greek letters for that, for what it's worth. This, however, didn't describe the universe Einstein thought it was, so he added a term to keep everything from collapsing. This term put a small repulsive force on everything. Was not strong enough to affect smaller scale things like planetary motions, but was able to build up on a scale of the universe to keep things apart. He called this the cosmological term. But in only a few years, Einstein regretted including it, calling it his greatest blunder. This was because the idea of a quasi-static universe was found not to be true. Edwin Hubble, the eponym for the Space Telescope, forced us to give up the idea of an unchanging universe. Starting in 1929, he discovered that the universe was actually expanding. You know, Hubble gives me faith in humanity. He started out as a lawyer, but became an astronomer. So there's hope. He discovered that many of the fuzzy cloud-like objects astronomers saw, which they called nebulae, were actually entirely separate galaxies, like our own Milky Way. In addition to being enormously further away than the stars in our galaxy, they were moving away from us much faster, with a speed proportional to their distance. He determined the distance from assuming that Cepheid variable stars were a standard candle, that is, of known fixed brightness, in which case you can determine the distance simply by knowing how bright it is where you are and figuring it out, okay? So a little bit more about that later. So he determined the speed of the galaxies from the frequency of the light we see from them. If the galaxies are approaching us, their light would be squashed into a higher frequency, that is on the blue side of the light spectrum. If a galaxy is moving away from us, the waves will be stretched out to a longer wavelength. That is the red side of the spectrum. Hubble found all the galaxies were going away from us. He found the linear straight line relationship between the distance and the speed of the galaxies, showing that the universe is expanding. Unfortunately, the original expansion calculation that Hubble came up with was off by a factor of 10 due to some experimental problems. And this led to the age of the universe of 1.5 billion years, which was actually less than the known age of the Earth. Quite an embarrassment at the time. Later, type 1 supernovae were found to be much better standard candle in determining distances to galaxies. This photo is of a galaxy with a supernova nearby. It occurs in the very rare case where a white dwarf star receives matter from a twin star until the white dwarf has received a critical amount that makes it heavy enough to collapse under its own gravity and then explode with a supernova. This explosion is about as bright as 5 billion suns and comparable to the brightness of a whole galaxy. It's also very, because of this critical amount of mass, it's also very reliable brightness. So we can know very well how bright something was to begin with. By the way, supernovae are very important to us because not all the elements were formed in the Big Bang. Only hydrogen, helium, and a little lithium. All the rest of the elements were formed in the interior of stars. And the only way for those elements to end up in you is to have the stars explode. You are star stuff. And the atoms in your left hand might easily have come from a different star than your right hand. So forget Jesus. Stars died so you could be here today. With supernovae as standard candle, the age of the universe has been found to be 13.72 billion years, to within about 1%. To illustrate this expansion, let's take a simplified two-dimensional universe. Imagine a two-dimensional array of galaxies at two different times. For simplicity, let's imagine that they are a grid of equal distances apart from one another, and the separation of galaxies at the earlier time t1 is smaller than a later time t2. Now choose a home galaxy to center on, the right dot, the white dot. Now overlay the two arrays and notice that all the galaxies seem to be moving away from the home galaxy, and the speed, that is a separation of the white and orange dots, is proportional to their distance from the home galaxy. Now choose a different center over here and overlay on that. And then the galaxies will all appear to be going away from that center with a speed proportional to its distance from there. So everywhere is the center of the expanding universe. Of course, the real universe has 3 dimensions. But when you're thinking of this, try to imagine that you were inside of it and not looking at it from outside, because it's not a very easy thing to do. But you've got to remember that this is only a simple two-dimensional. It's very hard to draw or imagine it in 3 dimensions, but that's what it is, what's happening. So actually, there was someone else who thought of this expansion before Hubble, but Hubble still gets more of the credit. Georges Lemaitre, a Belgian priest and physicist, published a paper in 1927 proposing the universe was expanding, but in an obscure journal, so it didn't get much attention. Also in 1931, Lemaitre came up with the idea of the Big Bang, projecting galactic expansion back to a single quantum. And the Pope picked up on this, promoting the idea that this supported Genesis, until Lemaitre pointed out to him in a letter that the Big Bang happened whether you like it or not, and that it could also explain the universe back to the origin without Genesis. After that, the Pope shut up. So the universe is expanding, but what will happen to it eventually? In a universe with an energy density dominated by matter, it is closed and destined to fall back on itself in a big crunch, reversing the Big Bang. A universe of low energy density is open, and the expansion will go on forever at a finite rate. At the boundary is a flat universe where the expansion will slow but never quite stop. So can we weigh the universe to tell what geometry we have? Yes. It's done this way. This is a galactic cluster. General relativity tells us that gravity is a distortion of space by masses. This means that light will be bent by masses it travels near. Very large masses can act as lenses and actually focus light. This is known as gravitational lensing. And we can use gravitational lensing on this cluster to determine its mass. This photo includes these blue light areas, which are actually various images of a galaxy that it's beyond, a galaxy beyond this cluster, that is the light is being bent around to form these images. And you can actually use that to determine the mass. So here's a plot of the mass versus position based on that lensing, and you see that the galaxies are these spikes here, but actually most of the mass is between the galaxies in this big lump in the middle here. And we have no idea what kind of mass that is, except it's not ordinary matter, and it's dark. It doesn't shine. So this sort of matter is called dark matter, because basically we don't know anything about it except that, you know, what its mass is. And it's far more, this dark matter is far more than ordinary matter here. And now if you take this whole thing and extrapolate it to all of the all of the galactic clusters, you can estimate the total amount of mass in the universe. And even including dark matter, it's only about 30% of what is needed to make a flat universe. So we have a problem. Do we live in a flat universe or not? Okay. So you can measure the curvature of the universe directly to find out. And here's how. This diagram is a representation of the history of the universe. And It's 13.7 billion years long. There's likely a period at the beginning of the universe where space itself was expanding much faster than the speed of light. Now, how is it possible since special relativity says you can't go faster than the speed of light? But that refers to the maximum speed in space. Space itself can do anything it likes. This early expansion period is called inflation. While there is still some controversy over its existence, it has gained considerable support over the last few years, especially from the discovery of the Higgs boson. The temperature during inflation was so high you could not form stable atoms. They would be immediately torn apart by collisions with other particles. In this boiling, it was a boiling plasma of particles, ions, that light couldn't penetrate because it would be immediately absorbed by another particle and re-emitted. However, when inflation had gone on long enough and the universe had expanded enough, the temperature cooled to where atoms could form. This is when light could propagate and not be immediately absorbed. So that is the first time we can see light from the early universe. It's what's known as a cosmic background, cosmic microwave background, and it's the afterglow of the Big Bang. And remember, the diagram here is not exactly showing the whole picture. Again, it's coming from everywhere. You're in the middle. You are now in the middle of this expansion. You're not looking at it like the diagram from outside. I mean, the cosmic ray, the cosmic background, microwave background is all around, all the way around, coming at you all the time. So you should remember that in imagining this, what's going on here. So this first surface where we could see light, where the universe had cooled enough, is called the last scattering surface, since it's the oldest time where it can see light. The temperature is about 3,000 degrees when the universe was 400,000 years old. But what we are seeing now, 13.7 billion years later, has cooled around 2.7 degrees Kelvin. This background radiation is extremely uniform, varying only about 1 part in 10,000 from the 2.72 degrees Kelvin. Now, there's some small lumpiness in the background radiation is from the limit where gravity can only travel at the speed of light, so it can only affect about 1 degree of the last scattering surface. So we can tell this lumpiness is about 1 degree. Now, what do we see when looking back at that last scattering surface? It's independent. It's dependent on the geometry of space that it has to travel in the last 13.7 billion years. If we have a closed universe, the size of these non-uniformities, these lumps, will appear to be larger than 1 degree. If our universe is open, the non-uniformities will be smaller. If the universe is flat, the lumps will appear to be about 1 degree apart, or in size of 1. So the top diagram shows experimental data of the cosmic microwave background from the boomerang experiment. The bottom 3 diagrams show simulations assuming closed, flat, and open universes. The flat universe clearly matches the data the best. This means that light has not been bent on its journey to us over 13.7 billion years. So we live in a flat universe. But we have just seen that the observable amount of matter, even including dark matter in the universe, is not enough to support a flat universe. So how do we reconcile this? Well, the answer is dark energy. This is a graph of experimental data showing the expansion of the universe using type 1a supernovae as a standard candle. The data show that the distance of the supernovae from us on the horizontal axis is roughly proportional to their speed going away from us on the vertical axis. That is shown as a constant slope in the upper graph, and a horizontal line in the lower graph where the slope has been subtracted out. So everyone doing these experiments at the time in the late 1990s expected the farthest galaxies, those on the right, to show that the universe was slowing its expansion due to gravity, which would show as a dip below horizontal at the farthest distances. Instead, the data is above the horizontal, showing an acceleration of expansion. That means that something is working against gravity to push everything apart, like Einstein's cosmological constant, to repel mass. This something that we know almost nothing about has been dubbed dark energy. How could the expansion of the universe be accelerating? It turns out that empty space can have energy. This animation is showing the space inside a proton, but away from the quarks, where the colored parts are virtual particles springing into existence and then vanishing in accordance with Heisenberg uncertainty principle. In this very small scale, you cannot know existence exactly. Rather, you can create particles as long as they don't last very long. But it turns out that 90% of the mass of the proton is in these virtual particles. And this is in the space not involved with the particles itself. So the quarks and gluons, it's empty space. So empty space can have energy. If you figure out how much dark energy is needed to account for the acceleration of expansion, it's exactly the 70% of the total energy needed to make a flat universe. So it turns out that 1% of the total universe is what we can see. Everything we can see is 1%. About 30% is dark matter and 70% dark energy. So the conclusion is that it's plausible that the universe came into existence from a state of nothingness in the Big Bang. Of course, this is not proof. Way too little is known about the early universe, and a detailed theory of quantum gravity will be necessary, a necessary minimum to explain the details, how it actually happened. But many of the elements are there. Stay tuned for this fascinating story as it's unfolding. Thank you.